All right. So, been through the syllabus here. We're going to start, as I said, the very first chapter that we're doing won't be in the book. I call it chapter 0 because it's kind of important information I want y'all to get. You probably had it in high school or in whatever various science classes that you've had here. But I just want to make sure that you got some of these down before we move on. Um, and the first of those are the standards for length, mass, and time. When we measure things, we can measure lots of different things, but usually when we measure things, we're measuring either length, a mass, or a time. All right, a distance, a length, a mass, how much mass something has, or the time, the duration of time. And in order to make those measurements, we have to have standards for those. Um, so when one measures a physical quantity, they compare an unknown measurement to a known measurement. That's every time we make a measurement. That's all that you're doing. You're comparing something that's unknown, the thing that you want to measure, to something that's known. And these measurements, that is, these known measurements, are called standards. And to have a good standard, we need three properties to be true. The first is that it is accurate. The second is that it is unchanging. And the third property of a good standard is that it is accessible to all, or to most at least. Accessible. I think that's spelled correctly. We need a standard that's accurate, something that measures that the known value is known really well, or at least to the amount that we need to make the measurements by. It needs to be unchanging. That means the standard, today it's this long, tomorrow it's this long. That ain't going to work. And then it also needs to be accessible. If I have the standard over here and I keep it and I never let you see it, then that's not a very good standard, because you can't you say, well, gosh, I don't know how to measure a meter, for example, because you got the standard and you're not allowing it to be released to the world. So those three properties are important for creating a good standard. And we'll see how those are applied to these three different standards for length, mass, and time. By the way, we're looking at the SI system. SI stands for System International. Or an international system, it's French. It's Système International. I think you've probably heard of the SI system, correct? We're going to use, in particular, a subset of the SI system called the MKS. And I'll let you try to guess what that means, or you might already know what it means as we go through the different measurements for length, mass, and time. Now, the current unit of measurement for length is the meter. I know what a meter is. It's a little bit more than 3 feet. This is a meter. People are about 1.5 to 2 meters, so I'm about 6 foot tall, and I'm a little less than 2 meters tall. All right, this is a meter. The standard has changed over time in the meter. For example, up till 1799, the meter was defined as 1/10 millionth the distance from the equator to the North Pole. From the equator to the North Pole. 1/10 millionth the distance from the equator to the North Pole. Now, which of these, accurate, unchanging, or accessible, which of these makes this not a very good standard? Is it accurate? Not really, right? It's hard to measure that distance accurately from the North Pole to the equator, and so it's just not a very accurate measurement. Is it unchanging, that distance? No, not really. It can change, right? As the Earth can sort of change its shape, geological formations can form. So it's not unchanging. It is accessible, excuse me, it is accessible to all because everybody can measure the distance from the equator to the North Pole. So of those, it is not accurate. So 1, 2, and 3. 1 says no. 2, it's also not unchanging. 3, it's accessible, but it doesn't meet those first two criteria. Now, until 1960, it was a bar in France. I know what you're thinking, right? What are you thinking? You're thinking, oh, it's a bar in France. It wasn't a bar like, hey, mister. It was a bar. It was a bar literally 1 meter long. It was a metal bar. I think it was platinum. It was a bar, and they said, this is a meter. This is a meter. We Frenchmen hold the meter. You may not see the meter. You may not touch the meter because it's very special. All right, so the bar in France is missing which of these? Is it accurate? It's sort of accurate if you want to know a meter. Now, if you want to know like tiny, tiny little measurements, like, I don't know, the width of an atom, maybe not so accurate. But if you want to know the length of a meter, then yeah, it's a pretty decent measurement. Is it unchanging? Yeah, sort of, kind of. Although we'll see with the kilogram a different problem. Is it accessible? No. So the meter in France, the bar in France, is it 1, 2, or 3? Maybe yes, maybe no. Is it unchanging? Okay, yeah, sure. Is it accessible? No. Although they would send copies out of this meter to all the different, countries where they made these measurements. And now the unit of measurement for the meter, the standard, is the distance that light travels in a certain amount of time. I'm going to write that time, but you don't need to memorize that time, though you do need to know what is the current standard for the meter. And it's the distance that light travels in this time, 1 over 3 times 10 to the 8 seconds. All right? Let me go through quickly, because I'm sure that you've had it. Scientific notation. Scientific notation, that 3 times 10 to the 8 is like a 3 with 3, 4, 5, 6, 7, 8 zeros behind it. So that is 3 times 10 to the 8. Right, I just multiply 3 times 10 to the 8, and I add 8 zeros to the end of that 3. Similarly, this is 3 times 10 to the 8. If I wanted to say 1 times 10 to the minus 3, this would be equal. I would take my decimal point and move it over 1, 2, 3 places. So it would be 0.001. That's scientific notation. You should have had it in middle school probably, but just so that we're clear and on the same page. All right? This standard, is it accurate? It's based on how we know the speed of light. And we know the speed of light very, very accurately. We can measure the speed of light very accurately. So it is accurate. The speed of light, as far as we know, doesn't change. And the speed of light is accessible to everyone. Anybody can measure the speed of light. I know it seems to you that that might be difficult, but all you really need is a little pen laser and a rotating mirror and a detector of some sort, like a CCD, and you can measure the speed of light. It's an undergraduate lab experiment to measure the speed of light. So it's accurate, unchanging, and it's accessible. All right. For mass, the current unit of measurement is the kilogram. Some of you might be figuring out what MKS stands for. What does MKS stand for? Meter, kilogram, seconds, right? It is a particular subset of the SI system. Now, many of you will not use the MKS system. Do you know what system you'll use when you go into your respective fields? Another subset of the SI system. Might not know. The CGS system. CGS is centimeters, grams, seconds, right? So like a cc, for example, that's a cubic centimeter. Or a gram, you might use grams or whatever, but some of you might use the CGS system, or you might use a combination of MKS and CGS. The current standard for mass is a cylinder, a particular cylinder. If you were to guess, where would you say that cylinder is? Somebody's going to guess? It's in France. It's a cylinder in France. Just like the bar used to be in France. They have like the National Institute of Measurements or something. I don't know what it's called. But it's in France. It's a cylinder in France. A problem with this is that the kilogram is losing mass. All right, right? So why is the standard for the kilogram not ideal? Is it the first? Is it 1? What is 1? Is it accurate? Yeah, sort of. Kind of like the bar was sort of accurate. That it's good if you want to measure something that's close to a kilogram, but if you want to measure, say, the mass of an atom, or say the mass of a whale, a kilogram's not a very good way to measure that. Kilogram is a little over 2 pounds, like 2¼ pounds or so. I'm going to pass this around, but this is sort of our standard for a kilogram. It's, your cylinder in France is sort of like this. It's just a piece of metal, and it says, this is a kilogram, everybody. Listen up. This is a kilogram. Okay? I'll pass this around. Taylor, right? So it's sort of accurate, sort of, kind of, maybe not. Is it 2? What was 2? Is it unchanging? We'll see. I'm going to show you a video from Veritasium. The kilogram actually is changing mass. They find that some kilograms are gaining mass and some are actually losing mass. So it's not unchanging. And is it accessible to all? No, it's not accessible to all. So not a very good standard for the kilogram, and that's why scientists today are trying to figure out a new standard for the kilogram, kind of like we've done for the the length, how we evolved from these different standards to now we have the standard that's based on the speed of light that makes it an excellent standard. Trying to do the same for the kilogram. Let's watch this video. This is from Veritasium, and listen, through the semester I'll show you various videos. For the most part, those videos are just sort of for your enrichment because I think they're interesting. And sometimes there'll be information that will be relevant that you'll need to know. Like, for example, here, you need to know what is the new standard for the kilogram going to be, and sort of what's happening. But as far as some of the other details, you don't need to worry about that unless I point them out to you. All right? All right. So standard for the kilogram is not ideal, largely because it's changing. That some of those standards that they've created are increasing in mass, and some of them are decreasing in mass. That it's not unchanging. Now for time, the current unit for measurement, what's the unit for measurement in the MKS system for time? It's the second. And the standard used to be based on the fraction of a solar day. From sun up to sundown. That has lots of problems for the fraction of a solar day. It is accessible to everybody, but it changes throughout the year. And then also, well, it's not very accurate when you're trying to measure things that are very short in time. Now we define the second based are defined on the period of an oscillating cesium atom. All right, so we have the cesium atoms. It has a very regular frequency or period. That is how fast it goes back and forth. And if you know that frequency and you know the number, I forget it's something like 10 to the 9 oscillations or whatever, then that is a second. That the cesium atom oscillates this many times back and forth in a second. And we can very accurately measure that period, the time for it to go back and forth. So that is the unit or the measurement for our time. Let's try a clicker question. I understand not all of you have your clickers today, but that's okay. Which of these is a reason that a standard of measurement is not appropriate? We are using frequency AA on your clickers. That is the default on your clickers. If you have questions about that, first just ask me. All right, so which of these is a reason that a standard of measurement is not appropriate? Give you 4 reasons. One or more than one of those is a correct answer to those questions. That it is not appropriate for which of these reasons? All right, we'll stop in about 5 seconds. At 45, 45. B is the right answer. Is the standard changes, that means it's not appropriate. And then if the standard is not available to everyone, that means that it's not appropriate. Those other things, the standard is based on some obscure physical constant. In fact, our standards are based on some obscure physical constant. The speed of light, the frequency of a cesium atom, the mass of a silicon atom, which is this new one that we're developing, or that scientists are developing. So, and if it smells really bad, of course, that doesn't really matter either. All right? Okay, let's see. There was one other thing, sort of as an aside, I wanted to sort of prep you for it. You will need to know some of our metric prefixes. And Derek in that video talks about some of the metric prefixes. You should have seen this at some point, but just let me remind you of them because you will need to know 3 of them for this class, and then you'll also encounter some others. So the metric prefixes that you'll need to be responsible for are milli, centi, and kilo. All right. The abbreviations for these are M, C, and little k. And milli is 10 to the minus third. Centi is 10 to the minus 2. And kilo is 10 to the third. All right. You'll also encounter these. You need to know these. But you'll encounter some others as we go along. You'll encounter micro, which is a lowercase Greek letter mu, and it is 10 to the minus 6. And then you'll also encounter mega, which is a capital M, which is 10 to the 6. You don't need to memorize those, though you will encounter these on quizzes and exams and stuff. The milli, centi, and kilo. Those are the 3 that you need to know. You'll encounter these as you read and what have you, but you don't need to know them. You might also see giga when we get into a later chapter. That's a capital G, and it's 10 to the 9th. All right? But the ones in the blue are the ones you need to know. Let's try a little activity for standards. You're going to break into sort of 3 groups roughly, sort of this side of the classroom, these middle 2 rows, and these middle 2 rows. And then within those 3 groups, you can break into groups of 2 or 3. All right, so sort of grab somebody, and what you're going to do is I'll give you some string. I have some string and scissors, and I have a few standards, and I'll put one over here for this side. I'll put one right here for the middle group, and then the third group, you'll use this standard. And what you want to do, you can't take the standard with you, right? You can visit the standard and make measurements of it and have some string if you want. You can use that string in some way. What you want to do is to measure the width of this room. And then we're going to come back together in about 5 or 10 minutes after you measure the width of the room, and we'll record all those values that you've measured. You follow what I'm saying? You're going to come look at the standard, take some measurements with it if you want, but don't take it away from the place. Use some string and scissors if you want to use that. I'm winking. Did you see me wink? All right. And then measure the width of the room. All right. You'll need to sort of spread out, and if you need to move the desk, that's okay, but be careful with people's things. All righty? Y'all clear? Y'all use this standard. Y'all use this one, and you guys use that one over there. String and scissors right here. Great. Yeah, you can take it but just return it as quickly as possible, okay? That's fine. You can take that with some scissors over to your standard. Or are y'all in groups of 2 to 3? Okay? String, scissors here. Just take off more than you need and cut it off. And then go with that. That's probably enough, Alex. All right, somebody can take Alex's string there if they want. All right, are y'all working together? Awesome. Is that, what is that, Amber? Is that a meter? It looks short. All right, y'all need some, you're waiting on string. Y'all waiting? Y'all come on over. Myosha, who are you working with? What's your name? Alea? Thea. Alright. And you're, huh? Khadijah. Lexi? Alexi. Lexi. Yes, okay. And Lydia. Right. Dre? Dre, is that right? And Daisy? Kai, right, Kai. I'm sorry, I shouldn't have stopped y'all, right? Should just let you fail with it. All right, you want to know the length of this room in meters, please? In meters. When you get your measurement, just come on over. What's up, ladies? Okay. The width, this distance, the shorter distance of the room. Come tell me, yeah. What 8 point what? Can you estimate? What's your name? All right, I'm going to put you next to it, okay, Maria? And what group are you in? One middle group, all right. I'm going to call y'all group two. All right, young. Jay, y'all have a number? What's the width? Okay.